Okay, we're gonna continue on here. Last time we finished up, I think, the nuclear chemistry chapter, if I'm not mistaken. So we're gonna bypass 19, I think I said. So we'll go to 20 next, which should be hopefully transition metals and coordination compounds. So a majority of this chapter is gonna be on really coordination compounds and complex ions. But we already got to the beginning here, gonna talk a little bit about transition metals, and some of it will probably be review for you, because a lot of cases are complex ions, as we will see, are usually a metal ion, and surrounded to that, they're attached to several molecules or ions attached to them. And a lot of cases, our complex ions will have a transition metal that will be sort of in there. And so we're just going to kind of review some of the things about transition metals. And again, most of it will probably be a little bit review. And then we'll get into really coordination and compounds and complex ions and all that good stuff. So let's start with some important sort of trends and things that occur on the periodic table and help us understand what happens with some of our transition metals. And one of the first sort of trends is was referred to as effective nuclear charge, or Z effective. And Z effective really is related to the charge that electrons feel as a result of the attractive force between the positively charged nucleus and obviously the negatively charged electrons. So there is that electrostatic attraction between those oppositely charged particles. And when we talk about electrons, as we know from, say, bonding and situations like that, there are certain electrons which are involved in bonding, and there's certain ones that are not really involved in bonding. And a lot of that has to do with a lot of these periodic trends and sort of what's happening. And if we look at something, for example, in terms of Z effective, it does increase in general as you go up into the right on the periodic table, and decreases as you go down into the left. So we take something and look like our friend lithium, which has three electrons, a little electron configuration, one s2, two s1. That means that essentially there are two types of electrons that we typically come across, as you may know. And those that are in the highest energy level, those are what are referred to as valence electrons, right? And those are the electrons obviously involved in bonding. They're not held as tightly, as we'll talk a little bit about here again. And they are basically involved in that because they can be sort of removed. They can be sort of shared in terms of covalent bonding. We also have ones that are closer to the nucleus, which are sometimes referred to as core electrons. So when we look at something like lithium, because it has an atomic number of 3, it essentially means it has a positive 3 charge. And when we talk about attractive forces in terms of electrostatic attraction, the strength of that electrostatic attraction does increase with sort of charge. So if you have like a +3, -3 sort of attraction, that's going to be a much stronger sort of attraction than, say, like a +1, -1 sort of attraction that occurs. So if we look at lithium, it has two electrons there on the first energy level. That again is what that first number means. That's basically our n equals 1, right? Ground state closest to the nucleus. It's got a couple of electrons flying around randomly there in the first sort of energy level, closest to the nucleus. Here on the second energy level, which is what the 2 represents, it also has its valence electron that is basically flying around as well. So the idea here is when we look at the sort of differences here, there's a pretty simple example here of our sort of valence electron versus our core electrons here. We can see that these electrons on the lower energy level, there's really nothing in the way of it being close to the nucleus. So what it feels is actually that kind of full brunt of the +3 attraction. So those electrons are really feeling that really big, strong, high +3 attraction. That's going to clearly move those electrons in closer because of that attraction. Now, when we go to our valence electron out here, this little guy right there, this valence electron actually is not going to feel the full brunt of that +3 charge. And that's because he's going to experience what is sometimes referred to as shielding. And pretty much what it sounds like, these lower energy electrons are essentially shielding that higher energy electron from the full sort of brunt of that +3 charge in this example here. So we can calculate what is referred to as the effective nuclear charge, effectively what that electron is feeling in terms of a positive attraction to it. And we can do that by basically calculating it by taking the atomic number of protons, which is +3, minus the number of electrons that are shielding that guy, which is 2. And effectively, instead of feeling a +3 charge, that outer electron there is actually only feeling sort of a +1 attraction towards the nucleus, which means it's not going to be pulled in as tight, it's not going to be held as tight. And that is why, one of the reasons why, right, we see valence electrons involved in bonding, because they're easily removed because of that sort of weaker attraction to the nucleus, because of this sort of shielding that occurs. Electrons in the same energy level don't typically shield each other. It's just those guys in a lower energy level will shield those electrons in a higher energy level. In terms of sort of the trend, as I said, it does increase as you go to the right on the periodic table and up. If you think about it, as you go to the right on the periodic table, the atomic number increases, and the atomic number increases means there's a lot more protons in the nucleus, bigger positive charge, and we're going to get this bigger sort of attraction to the nucleus that's going to happen, even to those outer electrons. So the Z effective for those guys on the outside, because the nucleus has a lot more protons, a bigger positive charge as you go up and to the right, it will feel, even those outer electrons, a much stronger attraction than as you go to the left there on the periodic table. And that's what we see here. If we look at sort of the trend here from sodium, magnesium, and aluminum and silicone, that is period 3 there on the periodic table going across the periodic table. And we do see that the Z effective as you go across the period does increase. The end result of that is it is related to the size of atoms that we see. And as we also go up and to the right on the periodic table, the size of the atoms gets smaller. And that is because a greater effective charge, even those outer electrons are feeling a pretty good pull to the nucleus, is going to bring everybody in closer to the nucleus. And the result of that is we see that the radius or the size starts to decrease as you go from left to right on the periodic table, as everybody just kind of gets pulled in closer. So even those outer electrons, because of the bigger positive charge inside the nucleus, will be pulled closer to the nucleus. And the overall size of our atom gets smaller, as you can see here. So the Z effective increases to the right. So even these guys here with those outer electrons are going to find themselves being pulled in closer, and going to make the overall size of that atom be smaller. Now, a majority of what we're going to talk about in this chapter will revolve around transition metals. In case you forget where transition metals are located, it is not there. It's between period 2 and period 3. These are our transition metals here. This is what it's sometimes referred to right here, going this way, as the first row transition metals. And transition metals have some unusual sort of properties. One of the ones you probably just know off the top of your head is the idea that it can have multiple charges, right? And that's why when we name these guys, say, like in type 2 compounds, we use Roman numerals to indicate the charge on the actual metal. There are only like 3 of them here that essentially have a fixed charge, and that's these guys right here. Zinc and cadmium, when they do form a charge, is +2. Silver is +1 if you hang a leftover there. And but all the rest of them will have a more variable type of charge when they do form charges. In addition, in terms of electron configuration, when we look at the periodic table, this is our S block, right? The first 2 groups. S could hold 2 electrons, right? Maximum 2 electrons. From group 3 to 8, that is our P block, and P subshell could hold a maximum of 6 electrons, since there's 3 different orbitals in a subshell, and each one could hold 2, 1, 2, 3, 4, 5, and 6. Our D subshell is down here in the transition metal region, and D subshell, there's 5 orbitals, each could hold 2. That is 10 maximum electrons when you do something like electron configuration. That's a 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And down here, this is our F shell. And F is 7 orbitals, each can hold 2. It's 14 total electrons if you max them up, and that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. You can count off electron configuration from the periodic table if you sort of know what you're doing. So this right here is our sodium, and it goes by period number. Period number is the principal quantum number: 1, 2, 3, 4, 5, 6, and 7. So if we were going to say sodium, which is right here, it'd be 1s2 all the way across to helium, 2s2, 2p6, and 3s1, which would be right there. If we were going to something like chlorine, which is right about here, we would do the same idea here. It would be 1s2 across, 2s2, 2p6, 3s2, 3p1, 2, 3, 4, and 5 coming across here. Remember that if you do count off electron configuration, you do have to be careful, as you roll into, say, something like a transition metal here. When you do go into transition metals, and if we were going to do that guy there, we would go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And you do have to remember that these start on the third energy level, which means that's actually 3D, not 4D. It is one behind the period number. That's 3D. That's like 4D, 5D, and 6D coming down. So that would be 4s2, 3d, 1, 2, 3, 4, and 5 if you're counting off sort of electron configuration. Also remember that this is technically 4f here and 5f, which technically go right about there because those are inner transition metals, and they are actually 2 behind the period number if you're counting that. So you can't count an electron configuration off the periodic table like that if you do know what you're doing. Most people are probably taught more of the zigzag sort of order of electron configuration, and that's something that you can make for yourself pretty easily by remembering that on the first energy level, there's just S's. On the second, there's P's. On the third are D's. On the fourth are F's. And pretty much you could just put the numbers underneath all these guys. So you could fill it in like 2S, 3S, 4S, 5S, 6S, 7S, 2P, 3P, 4P, 5P, 6P, 7P, 3D, 4D, 5D, 6D, and 5F. As you may know, you always start up here and you just keep following the arrows. The major sort of exception is it is the S coming before the D. So electrons do go into the S before they fill the Ds, and that pattern continues all through there. And that's probably the best way to sort of do electron configuration. It's really important, as we will see a little bit later on in this chapter, to be able to write electron configuration for some of these transition metals. We'll do some examples in just a second, but because you do need to know in certain situations how many electrons are in the d orbital for certain types of problems that we'll see a little bit later on in this chapter. Any questions on that there? So as we know, transition metals do show very good similarity as you go across a period. Also within a vertical group, they have very similar types of characteristics. They do have one oxidation state is usually found, more than one is usually found there. And they are, as I mentioned before, pretty much the most of the metals that you will find in these complex ions that we're going to talk about. And complex ions, again, is a metal ion that is positively charged, and a bunch of guys which are known as ligands. And ligands are Lewis bases. And if you remember when we talked about acids, a Lewis base is something that does what? Lewis base is like about electrons probably, yeah. And it is an electron donor, a Lewis base. And that is a Lewis acid is a electron acceptor. And that is, as we will talk about, pretty much the sort of relationship that develops with complex ions is oftentimes thought more of this as a Lewis acid base situation that's happening. And if you think about a Lewis acid being something that's an electron acceptor, if you have a positive ion, the only way you become positive is you lose electrons, which means you're electron deficient and you're willing to accept electrons in that case. So that's why they're very good Lewis acids, the metals, ions. And the ligands, again, are Lewis bases. So these are guys that have lone pairs of electrons and typically are polar, that they're able to donate these things. Also, as we will see, a very good Lewis base is something that has a negative charge for the same sort of reason. The only way you become negatively charged is you had to gain electrons, which means you got some extra electrons perhaps to give to somebody else. And that makes something that's a really good sort of Lewis base, like Cl minus, for example. Chloride is a good Lewis base as well. Water, as we will see, is also a pretty good Lewis base because it's got those non-bonding electrons on the oxygen, and it is polar, which allows that to work really well. And that's what we see here. This is our cobalt in the middle, and each of these ammonias are ligands, are Lewis bases. And in the case of ammonia, it works really well because ammonia, if you draw it out, it's got those non-bonding electrons on the nitrogen, also polar, so it works really well as a Lewis base. And again, our cobalt there is electron deficient, so it's able to sort of accept all those things as well. The overall charge here of this guy is a +3 charge, and that is because NH3 is neutral in all those cases. So the +3 charge is coming from the cobalt, which is electron deficient. By the time we're done with this chapter, you'll know how to properly name this guy here, rather than just saying that thing right there, whatever that thing is. You'll call it hexamine cobalt 3 ion, and we'll talk about how to name this guy and other coordination compounds, which, as you will shortly see, is a name that's like that long, probably. They dig up the whole page and just keeps going. So as I talked about before, ionic compounds with transition metals, a lot of these guys will have some different colors. And that's again because the transition metal and the complex ion can absorb light at different wavelengths. A lot of them are also paramagnetic. Paramagnetic means unpaired electrons, perhaps. Diamagnetic means they are paired up, right? Your spins, unpaired, heading in the same direction, paramagnetic. And depending on sort of the transition metal that's involved, you may have certain electrons, and in complex ions, they are sometimes separated or sort of distributed differently depending on the complex ion, depending on the geometry of that complex ion as to how the electrons go in there, and also the presence of a certain ligand or not ligand could cause the electrons either to kind of pair up or not pair up depending on what they're attached to. And we'll see that a little bit later on in this chapter as well. So we talked about electron configuration, and again, when we look at electron configuration for transition metals, as you know, and as we just talked about there, it is the 4s that does get the electrons, for example, first in that first row transition metals, and then we do start filling up our d orbitals, right, one at a time, and then coming back and pairing up in terms of how they go. That is obeying Hund's rule, maximum amount of parallel spin first, and then coming back and pairing up in that situation. So if we look at something like chromium and copper, these are two exceptions to the electron configuration. That if you wrote the electron configuration sort of following the normal sort of pattern, if you looked at something like chromium, which is 24, you would end up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. The exception with chromium and copper happens here at the end. It's been found to be more stable with one extra electron up into that d orbital. And when we look at something like this, it is not that big of a deal in terms of energy because these orbitals are pretty close to each other in terms of energy to begin with. And it doesn't take much for that electron to sort of promote itself upwards into that d orbitals. That also does maximize parallel spin for everybody, fills up all the d orbitals and makes it perhaps a little bit more stable. The same thing happens here with copper. And again, up until this point in the electron configuration, that is 18, that is argon's configuration. And that is obviously our shorthand that we have here. That's usually a noble gas that goes into those brackets right before whatever element you're writing electron configuration for, and then you continue on. So you can see here, one less electron in the S and one more in the D in both of those cases. Those are probably the two common ones that most people are told they have to remember, but you might have also been exposed to the idea that if you go below chromium and copper on the periodic table, even in from there, there's a lot more similar exceptions like this. Silver, for example, is an exception. PD up there has no electrons in the S. They've all been promoted up to the D. So there's a lot of exceptions really underneath chromium and copper in that transition metal region in terms of electron configuration. And it has a lot to do with the idea of how close these orbitals are to one another. Now, in addition to that, something else that you may also remember is once we actually start filling the d orbitals with electrons, although the 4s is lower in energy when the electrons go in, and we start putting electrons into the d orbitals, there's actually a switch in terms of energy of those orbitals, and the 4s electrons actually end up being higher in energy than our d orbitals, for example. And that's really important in terms of what happens when transition metals actually lose electrons. So representative metals will typically lose the last electrons in your electron configuration, and they will then drop back to the noble gas that comes before them in terms of their electron configuration. Transition metals are a little bit different. They actually will delve always into the s electrons first when they lose electrons, because they are highest in energy after the D's start to get them. And then if necessary, they will then start basically dishing into the D orbitals to take out some more electrons for however many that they need to lose. Also, when you think about valence electrons and transition metals, when you think about valence electrons, it does equal the group number. And when we look at transition metals and we want to think about how many valence electrons that they have, it also equals the group number. And it is the kind of just 1 through 18 group number numbering, where this is 1, 2, this is 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And that's how much valence electrons that these guys have. So if we looked at our chromium that we just saw, which was argon 4s1, 3d5, that is 5 and 1 is group number 6. And that would be how many valence electrons it has. If you rolled over to cobalt here, which is 27, that would be argon 4s2, 3d7 there. That is 7 and 2, which is 9, which would be how many valence electrons it has. Now, transition metals, when they do lose electrons, unlike those representative elements, again, will not typically get back to noble gas configuration, because we don't see like a plus 12 situation happening or anything like that, usually in terms of charges and stuff like that. So they don't necessarily get back to electron configuration our noble gas configuration, but they always will lose those s electrons first before they go into the d electrons to fix that situation. And that's really important in terms of how they lose electrons. That's also why sometimes you might have seen electron configuration written in terms of um, kind of like an order. You'll see like, all the threes together and then all the fours together. And that's usually electron configuration written based on energy, which pretty much nobody usually does. They usually write it based on filling order where the S comes before the D and stuff like that. And that's usually how you should write electron configuration. But sometimes people will show it based on energy. Any questions on that there? So again, as I mentioned, when they go to lose these electrons, we're going to take out the S first and then go into the D. So when we look at something like Ti, when it loses 3 electrons, these are going to be the first ones that are lost. And then we're going to come out of here and take out 1. And that would give us argon 3D1. So this is really important to understand how to write electron configuration for things with charges, because again, there are going to be places here where you have to figure out how many electrons are in that ion that's in the middle and how many specifically d electrons are there. And you also need to understand again how they properly go into the orbitals in terms of filling, that they do go one at a time before they come back and fill, because there's going to be a lot of questions of how many unpaired electrons do you have, or how many paired electrons are there, and that type of stuff. So when we look at something like iron, which is 25 there, I think, 26 would be better. That's going to be argon 4s2 3d6 here. And when iron loses 2 electrons and become +2, it has 24. So the correct configuration for iron with a +2 charge would be argon 3d6. And iron has the ability to very commonly become a +3 charge, which means it has 23, which then means we need to go into there and take out 1, and that would leave us as 3d5. So it's also important to understand that, if you have an iron in the middle and it's +2, it's got 6 electrons in those d orbitals, versus iron with a +3 only has 5. And again, we're going to talk about how they get distributed there. Any questions on that there? So why don't we do, I don't know, why don't we do nickel with a +4 charge? Nickel with no charge is 28, I believe. So if we look at just nickel with no charge, if you went old school here, 1s2, 2s2, 2p6, 3s2, 3p6, a little 4s2, 3d8, I believe there action happening there. And again, up until this point there, that is argon. So you could argon it 4s2, 3d8. Nickel with a +4 charge means that it has lost 4 electrons. That's what the positive charge means. So you're looking at 24 in this case. We definitely are going to take the S's first, and we also would have to dig in there to take out 2, and that's going to leave us an argon 3d6 in this case. And in this particular case here, our nickel would have 6 electrons, d electrons to sort of play with. Any questions on that there? Yeah. So to finish up talking a little bit about some other periodic trends and sort of transition metals, some of the things we talked about in some of these previous chapters are oxidation states, and you can see MN has a ton of oxidation states. For the most part, most of these guys here in the first row, transition metals, typically will be +2 or +3 are very common oxidation states. It does sort of increase as you get towards the middle there of the first row, and then kind of comes back down a little bit in terms of oxidation numbers. But a vast majority are these kind of +3s and +2s that most of these guys are typically going to sort of form. Now, ionization energy is the energy required to remove an electron from a gas state of an atom. When we talk about ionization energy, typically we think about cations, and that's because those guys are positively charged, right? So it's the energy basically to remove those electrons. In general, the ionization energy on the periodic table increases as you go up and to the right, decreases as you go down. As you may also remember when you probably talked about this, electrons do not just all come off at once. They come off basically one at a time. So if we looked at our friend magnesium, the first thing that would happen is magnesium would drop one electron, and that would be known as first ionization energy, which is the energy required to remove that first electron. Then this guy that's already lost one electron would then lose a second electron, become a +2 charge. And the energy required to do that is what is referred to as the second ionization energy. And then maybe he takes one more electron off, become a +3 charge, plus an electron. That would be the third ionization energy. So there is a sort of ionization energy for each electron that basically comes off. And as you could probably imagine, as we go from first ionization energy to second to third to fourth to fifth to however many, it does get progressively harder to remove those electrons. It does require a lot more energy to do so. And that's because when we lose electrons, say from our neutral guy, does the ion become smaller or larger when it loses an electron? Becomes smaller, loses electron cloud, right? Everybody becomes smaller because now those outer electrons are going to feel the greater positive charge of the nucleus and get pulled in closer. The result of that is they're going to be pulled in closer and held tighter, which means when you try to rip off the second electron, it's going to be a little bit more energy to do so. And then obviously it's going to get smaller again and get harder and harder to continuously pull off electrons. So in general, the first ionization energy is usually smaller than the second, then the third, then the fourth. It takes more and more energy every time you try to sort of remove an electron. And that's what we see here. If we look at this is the first ionization energy, second, third, fourth, and so forth. When we look at something like magnesium, which is 12, 1s2, 2s2, 2p6, 3s2, when we take off that first electron is 735 kilojoules of energy. Then it kind of doubles to 1400, which means it's twice as hard there to rip off the second electron. After we get done with the second electron, which is all the valence electrons, by the way, we're now into core electrons, and you can see we now got like a 6 to 7-fold jump there in terms of energy to try to remove that core electron. And good luck with that. It's pretty much not going to happen energy wise because they're too close to the nucleus. They're held too tightly. It's just not energy efficient to do so. That's why when we think about magnesium, it is not a +3. It stops right there at +2, as that is the last valence electron that's there. And that's the last one that's sort of easier to remove than before you get to those core electrons. Also, why when we look at aluminum is +3, because first one is 580, then a pretty good jump on the second one, and then a pretty good jump on the third one. Now you're into core electrons and you go from 2,700 to about 11,000. That's a pretty big jump in terms of energy, and it's not going to really happen. And that's why aluminum has sort of a fixed charge of +3, because once you get into those core electrons, you're probably not going to be able to remove those electrons pretty easily. Here are some trends in terms of our transition metals. Obviously, as you can see, atomic number increases to the right. We also talked about the size getting smaller as you go to the right. There's our ionization energies, our common oxidation states, +2s and +3s. We also see density increases as you kind of go to the right as well. Um, And here's just pictures of our first versus third ionization energy, and obviously much higher for our third ionization energy than our first, harder to remove that third electron, and there's the second one in between there. Now, electron affinity is the energy change that occurs when somebody does gain an electron. And we usually think about electron affinity with anions because those are guys that will gain electrons and become negatively charged. It is different than electronegativity. Electronegativity is the ability of an atom to bring electrons towards itself. Electron affinity increases as you go up and to the right and decreases as you go down. It's not a perfect trend, but that is a general trend that we see. This is basically group 7 here. And we do see as you go up, it does increase, but again, not a perfect trend as it kind of comes back down a little bit. Affinity means you usually like something or good at something, right? So these are things that like to gain electrons. And that also does sort of go with our electronegativity, as you should know. Also increases as you go up to the right and decreases as you go down, with fluorine being the most electronegative element that we have. So all those things that we see here basically relate to why we think about nonmetals as gaining electrons, hanging on to electrons, and metals, right, losing electrons and not really hanging on to them too tightly. There's that as well. This is the relative reducing abilities of the first row transition metals, and reducing ability increases. So if something has the reducing ability, it's going to be oxidized. So this guy would be would be most likely oxidized or go through oxidation, while this guy down here would go through reduction. And you may say to yourself, this looks like the stuff we were talking about in electrochemistry, but I thought the one that's more positive is the one that gets reduced. And you are right, because when we looked at it, when we did electrochemistry, those were SRPs, right? Standard reduction potentials. All these are written as oxidation reactions, electrons on the right-hand side, sometimes referred to as standard oxidation potential. And that means if we reverse all these reactions and make them into SRP values, all these guys would then become negatives. And this guy would become a positive. And now the one that's more positive, like our SRP, is the guy that would get reduced in this case. So this is standard oxidation potential. And we could see that the reducing ability, which means it will go through oxidation, it will cause a reduction of somebody else, increases as you go basically to the left there on the first row towards SC. Any questions on that there? All right. Here's what each of those guys look like in case you need to pick them out in a lineup. All right. This is stuff that you don't have to worry about anymore because you don't do general unknowns in this class. So you should be happy about that. So we'll just kind of go through that without having to worry about it. All right, so that was some basic ideas, and again, some of that hopefully should be, or a lot of that should hopefully be some review for you in terms of transition metals. And again, the purpose of that is a lot of what we're going to talk about here in the rest of this chapter does involve sort of transition metals. So let's get into sort of that idea of it and a coordination compound. So when we talk about a coordination compound, you can really think of a coordination compound as really like an ionic compound. There's like a positive side and a negative guy. And just like in an ionic compound, the positive guy always comes first and the negative guy always comes second. Now, there's two parts to a coordination compound. There is a complex ion and there is a counter ion. And you can have a situation where your complex ion is positive, and to balance out the charge, your counter ion will be negative. And again, it would, in that case, the complex ion would come first and the counter ion would come second, positive, then negative. You could also have the opposite situation where your counter ion is positive and your complex ion part is negative. And again, in that situation, your counter ion would come first and your complex ion would come second. Now, a complex ion, as I mentioned before, is typically a metal. And again, a lot of times this is going to be our transition metal with our positive charge, which makes it, again, electron deficient. And a bunch of these ligands, which are Lewis bases, that are going to be able to donate essentially a pair of electrons to our deficient metal. So again, we do look at a lot of times this sort of coordination complexes are really more complex ion part of it as a kind of a Lewis acid base situation that is happening, where our ligands again are sort of donating these electrons over to the deficient metal. As I mentioned earlier, in order for something to be a ligand or a good Lewis base, it does have to have some non-bonding electrons. And a lot of times, if you do have some non-bonding electrons on some of these really electronegative type elements, and they are polar molecules, they are typically very able to basically donate those. Also, again, as I mentioned, things that are negatively charged will typically have pretty good ability to do that. By the way, when we look at something, and we go copper with a +2 and we write aqueous next to it, that's basically a copper ion that's floating around the solution. That copper ion is not really floating around in the solution by itself. It's actually attached to a bunch of waters are attached to it. And that is what the aqueous part of it is, basically. So I won't draw them all, but there are probably about 6 waters attached to it. And oftentimes we leave that part out when we write equations because it gets a little crowded with all the waters and stuff in there. And we just write aqueous next to it. But that's really what it means. It's floating around. It's not freely floating around in that solution. It is surrounded in really a complex ion sort of situation with the water molecules as it's basically bouncing around in the solution. Any questions on that there? Now, when we look at our ligands, there are certain ligands, and every ligand will have what is sometimes referred to as a donor atom. And that's basically the atom that is directly attached to the metal. It's really the guy that's got like the electrons and where it's attached. In the case of water, here is the oxygen that's going to basically attach to a metal. And in the case of NH3 is the nitrogen that's going to be able to attach to a metal. Now, the number of donor atoms there are that are surrounding the metal in a complex ion is what's known as the coordination number. And that is actually how many atoms are directly attached to that metal in the complex ion. So if we just had a made up one like what we got going on here that I just drew, directly attached to this metal is the oxygen and the nitrogen, and that would have a coordination number of 2 in this case. It's basically those two things that are attached. Now, the coordination number, for example, when you look at something, say like what I just wrote a second ago or was drawing a second ago, something like this, sometimes people think that the coordination number is always like this number here. And in the case of water, it actually would be, because when water attaches to the metal, it is what is referred to as being a monodentate ligand. And mono meaning one. So basically, it has only one atom in it that will attach directly to the metal. So if you did have 6 waters attached to it, the coordination number there would be 6, because every water would basically attach through the oxygen, and you would have basically 6 oxygen atoms directly attached to the copper ion in that situation. So here the coordination number would be 6. Now, there are certain ligands that have the ability to actually attach to the metal in multiple locations per molecule. An example of this is a bidentate molecule known as ethylendyl and abbreviated a lot of times in coordination chemistry as EN. So if you see like a little EN in parentheses, that stands for ethylendyl. It is actually used both in names and actually formulas. So people will use that abbreviation in both of those. To see what that looks like, I'll give it the old college try. Why not? It looks something like this, maybe a little bit of that. Is this feeling very organic-y? We'll do a little bit of that there. So that's ethylendyl, I think. Yeah, I'll go with that. And if we do have a metal, for example, that's going to attach, and that, by the way, is one molecule of it, it is actually going to attach through this nitrogen, and it will also attach through that nitrogen. And you basically get a 2-for-1 deal on that for every molecule that will attach in 2 locations, which means if I had another molecule of that, it would also attach through the nitrogen and through the nitrogen. And my coordination number for this guy would actually be 4. And when I would see it, say in a formula, it may just be like metal En2. And clearly the coordination number is not 2 in this case because the actual ligand itself has the ability to do a 2-for-1 situation. So you do have to be careful. It's not always, and sometimes people do that. They look at sort of the formula there and go, oh, it's always like the subscript. It's always the coordination number. It is if it's monodentate, but if it's bidentate, you do have to adjust for that. I would say ethylenediamine is probably a very common bidentate one that you come across, along with our friend oxalate C2O42 minus is also another very common bidentate one. And if you draw oxalate, it looks something like this. And it actually has the ability to bind to a metal through the single bonded oxygens that have the negative charge, and they will bind a 2-for-1 situation as well. So I would say those are two very common bidentate ligands that you come across a lot. And obviously, same deal there. If you had 2 oxalate molecules attached to a metal, you would have a coordination number 4. If you had 1, it would be a coordination number 2, and so forth. Any questions on that? Now, believe it or not, there are some ligands that go 3 or more, and those are sometimes referred to as polydentate. That is EDTA. And EDTA, as we'll see a picture of it in just a second, I believe has the ability to bind in 6 places per molecule. And it's a really good, sometimes referred to as a metal chelator, because one of those molecules is pretty much going to put a cage around a metal. It's going to pretty much surround it and grab onto it. And it's used for that to sort of tie up metals and stuff like that, because it has all these places where when it sees the metal, basically just going to bind and sort of put it into a cage and bond to it really, really well. Now, how do you know how many sort of ligands might bond to something or a transition metal? There are common sort of metal ions and the coordination numbers that they make. You can see here our guys that are sort of +1 will typically do more of a 2 in terms of coordination number, a little bit of 4. When you get into kind of the +2s, you get into kind of your coordination numbers of 4 and 6. Your +3s, larger positive charge, more electron deficient, able to accommodate perhaps more ligands, and you get more like a 6. Except for gold 3, we'll do a coordination number 4. So in general, kind of the larger positive charge, more electron deficient, going to be able to attract more Lewis bases and probably allow for more donor atoms to basically coordinate in there, versus something with a much smaller positive charge, not going to be as electron deficient, not going to need as many sort of negative electrons coming in. There's our ethylenediamine, as you can see there, and there's our EDTA. And you can see that in this particular case, this entire molecule is EDTA, bond once, twice, 3 times, 4 times, 5 times, and 6 times. It basically will cage up that metal pretty well there. And again, it's what is sometimes referred to as a chelating agent as well. In this case here, this is 3 molecules of ethylenediamine, or that En guy. There's 1 right there. There's 2 right there, and there's 3 right there. And in terms of the coordination number on the guy on the left, it is 1, 2, 3, 4, 5, and 6. Again, we have 3 bidentates. 3 times 2 is 6, would give us our coordination number there in this particular case here. Also does a pretty good job with those 3 of them, kind of like what one of these EDTA molecules will do. If you ever look at ingredients on a lot of things, you'll sometimes see that listed as in part of the ingredients, and they use it sometimes. Here's a table of some common ligands. I'm not sure where the D went, but the ligands there. Here's our water, our cyanide, our ammonia, our NO2, our thiocyanate, our hydroxide, and our halogens. These are all monodentate. There's our oxalate and our ethylenediamine. There's also diene, which is actually 3 nitrogens. So every one of these guys here has the ability to bind in 3 places to a metal. So if you have a metal, boom, boom, and boom, it would bond basically in 3 spots there. There is EDTA, which is ethylenediamine tetraacetic acid. To help you, the bonus question, spell that, I suppose, right? Also, by the way, has a -1, -2, -3, and -4 charge happening there when we look at it. All right. So let's talk about this. What are the oxidation numbers of the transition metal in each of these coordinated compounds? And just so you understand sort of the way these things are written, typically speaking, when coordination compounds are written like this, we oftentimes will put our complex ion in the brackets. So the guy in the brackets is the complex ion. So why don't you take a second, figure out the oxidation state of the and a little AU and an OH and a 4. All right, so as I mentioned before, typically speaking, when we write these coordination compounds, a lot of times complex ion will be put in these brackets. So right off the bat here, when we look at this, we know this part of it here is our complex ion. Remember, in a coordination compound, you will also have a counter ion, which would have to be this guy there. Now, when we go to assign sort of our oxidation states, we just do it kind of like normal. So we have OH there, which is hydroxide, and each OH is -1, and there's 4 of them, which means we got like a -4 sort of happening over there. Out in front is potassium, which is group 1, and it has a +1 charge. Remember that overall here, this is all neutral, which is typically what a coordination compound will be, which means in this case, the gold does need to be +3 to balance everybody out to 0 in this particular case. So +1 on the outside, +3 there on the inside with the gold gives us +4, with the -4 coming from our hydroxide. Any question on that there? Now, if we look at the second one here, we have our brackets coming out first here in the formula. And we got a little parentheses here. So in this case, this front part here is actually going to be our complex ion. This then would be our counter ion in this case. So we could still start the same way. NH3 is 0. Yes, not +1 because that's not ammonium, right? So that is NH3, which is ammonia, no charge. That's nitrate out here. That's a -1. There's 3 of them, which means that's a -3. So our metal here to balance it out would actually also need to be +3 in this case. Yeah. First off, any questions on the sign of the oxidation states? All right. Then when we look at the complex ion here on the left, what is the coordination number? Coordination number is it is 4. There are 4 hydroxides basically attached to that gold metal in the middle. That is our complex ion part. So we essentially have the gold and 4 of these hydroxides attached, right? And since hydroxide is monodentate, the coordination number there would be 4. How about on the right here for our complex ion on the right? It is 6. Same idea. We have chromium there, and we have 6 of these ammonias attached through the nitrogen only, since it's monodentate, which means we would have, again, a coordination number here of 6 basically happening. Now, when I look at my complex ion part here on my left-hand side, what is the overall charge of just the complex ion part? It is -1, as this is +3 and this is basically -4. That is a -1 overall for my complex ion. That is a negative complex ion. That is why when I look at my counter ion here, I just need one potassium ion to balance it out. That gives me +1 and -1, gives me 0 when I put them together, right? So that is what's happening in this case. When I look on the guy on the right, the overall charge of my complex ion on the right is, it is +3, as this is +3 and this is 0, which means this is +3. That is why on this one, when I look at my counter ion, I need not one nitrate, not two nitrates, but I need three nitrates to give me a -3 charge to balance out the +3 charge there on my complex ion. In this case, my complex ion is positive. In the first case there, it is negative. That's actually really important to understand as well, because we're going to talk about here shortly how to name these things. And depending on whether your complex ion is positive or negative, you do name it slightly different depending on that situation as well. Any questions on how to figure that out? Now, when we look at the counter ions, again, they're just kind of put in there to balance out the charge in these guys. And as you can see, if we have that negative complex ion, we'll have a positive counter ion. And if we have a positive complex ion, we'll have a negative counter ion. But it does follow basic ionic sort of compound rules. Again, it's always the positive guy first and then the negative. So that's always the order at which you want to write it. Any questions on that there? So speaking of that, let's get into the craziness of naming. Yes, I know you thought all your naming days were over, but one more weirdness of naming to end it with, I suppose, or maybe not, but getting close. All right, so as I mentioned before, when we're naming these coordination compounds, we do go positive and then negative. Again, that's both for name and formula. So the cation guys first and the anion second. And as we just saw in that previous example there, it could be the complex ion positive or complex ion negative. So counter could come first, complex ion could come first. Within a complex ion, the ligands are named first in alphabetical order, regardless of any prefixes that may be there. So we do go alphabetical order first for all the ligands, and then the metal is always named last in the complex ion part of the name. So I say that because really you got to think about it. There's like a counter ion part of the name and a complex ion part of the name. And again, that could come first or second. So when you're talking about the complex ion part of the name, you should always have the ligands alphabetically, regardless of prefix, and then the metal part should come at the end. Now, the names of negatively charged ligands will tend to end with the letter O. Neutral ligands are usually called by the name of the molecule. There are a number of exceptions. So water is sometimes called aqua, depending on your book. CO is carbonyl. NH3 is amine. And there's some other ones. We'll see some tables here in just a second as well. Now, if you happen to have several ligands of the same kind, we do use prefixes. So if you have two of the same ligand, we use prefix for di. We use tri for 3, tetra for 4, penta for 5, and hexa for 6. So this is what I was talking about before. We do ignore the prefixes in terms of the alphabetical part of it when you're putting the ligands in place. If the ligand already contains a Greek prefix, then we roll with our friends bis for 2, tris for 3, tetrakis for 4. Could be making this crap up, but I'm not. To indicate the number that is there as well. You just think like the three guys in some other place that came up with all these rules. Now, what are we talking about there? I don't know. No, I do know, maybe. So maybe we tell you. That is like our ethyl endyl diamine. So you remember this guy from earlier that I drew, and it's called ethyl endyl diamine. In the actual name of that ligand, there is a prefix, di part of it. So if you had that guy and you had two of them, you wouldn't use di, but you would use bis in that case because the name of the ligand itself actually already has something like di in it. So that's what that means. That's probably the most one that you'll come across where you'll do that. I will say oxalate, which even in its sort of name that we use for oxalate, uh, doesn't necessarily have a prefix sort of in it. In a sense, people will sometimes use bis and tris if you have more than one of those for that guy as well. So it's sort of common as well. Also, another kind of unusual thing that we do and sometimes does occur with some of these coordination guys and complex ions is we do use the name of the metal, and we do include a Roman numeral for the charge on the metal. And this also includes ones that we typically do not use Roman numerals for, like our zinc, cadmium, and silver, which has a fixed positive charge. We actually still use Roman numerals for them in this type of naming. And as odd as it sounds, what I'm going to say, we will actually use, I guess it's not really Roman numeral, but if your metal has a neutral charge, which can happen in a weird situation, you would use like a parentheses and 0. So you would use that for it as well. So that could oddly sometimes come about, that you add up everything else and go, the oxidation state of my metal is like 0. So it is possible that you could have that, and you would kind of do like a Roman numeral with a 0, or parentheses, I guess, with a 0 as well. Now, this last one is where we come into the play of what we were just talking about on the previous slide, which is if the complex ion part that you have is negative, we actually roll with the old school name for the metal, which ends in ate. So instead of it being iron, it will be ferrate. Instead of it being copper, it will be cuprate, plumate, and that type of stuff. So we kind of use that like old school name that ends in ate for metals that are in a complex ion that's negative. If it's positive, we just roll with the regular name like iron, lead, copper, whatever it may be. But if your complex ion is negatively charged, you have to roll with sort of these older school names. So here are some other ligands in some of these tables here. So we can see water again is aqua or aquamine, methylamine, carbonyl are sort of halogens are named kind of like they normally are in most things. Fluoral for fluorine, chloral, bromo, iodo. Hydroxo for hydroxide, cyano there for cyanide. Um, Here's what I was talking about. If your metal is negatively charged, again, we get more of a ATE ending and sort of the root type name of it. So ferrate, cuprate, plumate, arurate, stanate, for these type of guys. Here's a few other ones that you might come across. There's our carbonate, our carbonato, and our oxalate or oxalato. Feel like I'm ordering coffee. I'll take a carbonato with an oxalato, maybe a shot of cyano. I don't know. These are some of the names that we'll come across. This is our ethyl endyl diamine, and like I said before, most people will use that abbreviation both in the name and also the formula as well. Uh, you can obviously write out the formula like I did earlier, but sometimes a lot of times people will use just that EN for there. This is actually EDTA here. That's EDTA. And you can see that is a mouthful right there, I suppose, right, as you go through that. So if we look at, say, the couple that we just looked at here, and we wanted to, say, name these guys here. So let's see, let's bring it back this way, maybe here. So we have K, and then obviously our AuOH4 in this case. So if we were going to name this guy, we would start, with the positive guy and then roll to our negative guy. And in this case, as we saw earlier, our positive guys are counter ions. So the nice thing about counter ions is they're pretty much just named like you normally would name it. So that's just going to be potassium, basically. And by the way, if you had two potassiums, just like if you had K2O, that's potassium oxide. It doesn't matter how many you have of your counter ion, you pretty much just use the name of it. If your counter ion is a polyatomic ion, you just use the name of it by itself. Doesn't matter how many you got going on. Now we get to our complex ion, which clearly we have seen is negative here, which means when we look at gold, we do need to go to our table there, right? And we need to use our sort of old school name there for gold. So we're going to use arurate. So we'll come back here. And we already know that that is going to be a Roman numeral 3 because that is the charge on the gold. We have 4 of these ligands, so the prefix for 4 is tetra, right? And now, right, we want to make sure that we use the proper name there for hydroxide. So again, that is our hydroxo there that we saw right there. So that is going to be hydroxo. And we'll put that together there. Now, putting it together, we will start in this case with our counter ion, which is our potassium. We're going to do now into the complex ion part of the name, which means it is our ligands to come first in alphabetical order. Since we only have one, this would be tetra hydroxo. And now our metal in the complex ion comes at the end. Rate Roman numeral 3. Kind of squeezed it in there. So that's going to be potassium tetrahydroxo rate 3. I was not kidding. It's like the whole page there in terms of that name. Yeah. Any questions on that? Why don't you try this one here? Why don't you give the name of the other guy there? Okay, so let's take a look at it. So we did a lot of the dissection earlier. And by the way, if you didn't do that and you just look at this, we always know positive before negative, right? So when we see the complex ion coming first here and our counter coming second, we automatically know that this guy's positive and this guy's negative just based on the way it's aligned in this formula. We already figured out earlier that this guy is a +3 charge. Because our complex ion part here, which is this first part, is positive, that means we could just use the regular name for chromium. We don't need to use the other name. So this is going to be a chromium Roman numeral 3, not 4, Roman numeral 3 there. At the end, we have 6 of these ammonia ligands, which is going to be this guy. Prefix for 6 is going to be hexa, and we're going to have an amine situation. And our counter ion here, again, regardless of how many we have, it's just going to be named by its full name. And this is our polyatomic ion, which is nitrate, basically. So again, putting this together, when we start with the complex ion part, we're going to start with our ligand. So it's going to be hexaamine. This is going to be then chromium Roman numeral 3, which is the metal that you come on the last part of the name, and nitrate in this case. Yeah. Any questions on that there? Now, what happens if we did not have our counter ion here? We did not have this part of it, and we just had this part. It pretty much would be this name exactly. Get rid of the nitrate, and you just put ion at the end. Yeah, so that's how you basically just name the complex ion by itself, the same way you would do. Just don't put the counter ion in there, and you just put the ion at the end of it. Any questions on that there? All right, we will lay it up there for today.